Hello, Charlie B here. Welcome to part 2 of cryptocurrency from scratch. If you recall, last time we created some transactions with no encryption, and we enforced that those transactions would be consistent in terms of the amounts of coins transferred. This time we are going to start adding some encryption so some cryptography, put it that way. This video is going to be mostly groundwork for creating the cryptographic primitives that we're going to use to sign, verify, generate addresses, and that kind of thing for the transactions. So let's do it. I've taken the liberty of putting all of the imports into my copy buffer because I don't think anybody really needs to watch me type all this out. So there we go. This is using the rather nice and quite friendly cryptography library in Python. Of course, the rule is with cryptography, unless you have multiple PhDs in mathematics and computer science, you don't try and write your own cryptography libraries. You use standard ones that other people have had a chance to review, and so that's what I'm doing. I don't think that would make a very interesting video for this audience to try and write a cryptography algorithm from scratch. Okay, let's leave this where it is. Let's change this to test transactions, and then we can just move all this stuff down basically. Def main. So this is our new main. We're just going to use it to test and run some of the cryptographic functions that we're going to create. But right now it's not going to do anything. Okay, so the first thing that we need to do is to be able to create a key. So this is going to be creating a private key, and we are going to simply return EC, which is elliptic curve, which is the cryptography algorithm that Bitcoin uses, and we want to generate a private key. Now with this you have to specify which elliptic curve you want to use. I couldn't tell them apart at all, honestly, so this is the one that Bitcoin uses. SecP 256 K1. Now this library, as you can see up here, has a couple of different backends that support different subsets, and some of them are implemented directly in the library, and some of them are implemented by external libraries. In this case, I'm just going to use the default library. Default backend, which I have to instantiate, and that's that. So let's see what that looks like. Print new key. Have to be in the right place. Okay, so that is not something that's going to be terribly useful for signing, because as you can see it's not what you might expect. It's actually just an object in Python. So we have to turn it into some text, and then it will start to look. If you've ever looked at a Bitcoin address or any other cryptocurrency address, you'll have some kind of idea of what they're supposed to look like. and that's what we want to get to for this. Not that this is an address, but the principle's the same. So I want to take the private key and turn it into text. And I'm going to do this by getting its bytes, private bytes. And I have to specify a whole bunch of stuff. Well, 3 things. But to specify which encoding I want to use. In this case it's PEM, and which private format I want to use. S8, is that right? Yes. And in this case I just want the raw private key, I don't want any encryption, so no encryption. Okay. And let's return that and see what that looks like. I'm going to do text. Yep, spelling mistake. Okay, so that's a little better. What we have here is it's an array of bytes, which this whole library basically operates on arrays of bytes. So any strings that we have are going to end up being arrays of bytes. And then it's got this with a carriage return at the end, and then a string of stuff with another carriage return and another carriage return, and then this part at the end. I don't really want that. I really just want this stuff with no carriage returns and no begin and end. So let's do some, call it string processing. So I want a bytes object, and I'm going to join these things. What I'm going to do is I'm going to split on carriage return, get rid of this one, get rid of this one, and then join all these guys together with no gaps. Okay, so that would be txt.split on \n, and I want 1 all the way up to -2. So 1 is this guy. So starting from 1, we're going to start from here, and this is -1 because Python can count backwards, which is really nice, and this is the end of this is -2, and I don't want either of those, so I'm saying start here at 1 and go all the way to the beginning of -2, which is here, and then join them up. Okay, let's see what that looks like. Not good. Okay, let's see, where did I go wrong? That's what I thought. So you can't split bytes with a string. There we go. Simple, relatively compact, and without any other bits and pieces hanging off it. So there we go. There's our private key and an encoding of our private key. Now, the next thing we want is to be able to do the same thing for a public key. And there's actually a better reason for doing this for a public key. With a public key, you actually need to write public keys into the transaction. And so this is what we're going to do with the public key. We are going to actually take a public key. I'll show you how we're going to use it, but the argument is going to be a public key. key, and then I think it's pretty much exactly the same. Not exactly. Okay. Key dot public bytes. The encoding is the same, so that's nice and consistent. And then public format, subject, public key info. That is again just the format of the output. I don't fully know exactly what that means, except that it gives me something that I can import and export, and to be frank, I don't care that much, as long as it works and demonstrates what I'm trying to demonstrate. I'm totally okay with it. So we're going to do the same thing. Let's see what it returns. I think it's going to be exactly the same, or very similar to what we saw before. Okay, so we're going to have to, let's do private key is new key. Let's make it a little, let's print, and let's do hub text, and it's key, I believe it's just dot public key. Double check that. Yep. What did I do? Oh yes. Got to balance those parentheses. Key is not defined. Of course not, because I didn't call it key. Yeah, okay. So it's the same thing, but shorter. So here is our private key, and here's the same thing with our public key with the end and begin and end blocks. So let's do exactly the same thing we did here. And we should get the private and public keys together. Ah, good. Okay. Now, what we do need to be able to do within our transactions is take this public key text and turn it back into a public key. So I'm going to call that text pub. We're going to get the text, and I'm going to wrap it in this stuff, like this. Okay, so this is, I counted this before, so I know. This is a 64-byte block to the first \n, which is here, and this is another one. 64, this is actually, the second part is 56 bytes. So in order to do that, we have to do text all the way up to 64 plus \n, which is a byte, \n, plus text. I want to do from 64 to 64 plus 56 plus the end block, which is this guy. Only with quotes around it, otherwise Python will have no idea what we're trying to say. Okay. Now that we have this, let's just put it in a variable. I know it's bad practice to reuse variables like that, but I don't care right now. We're only using it once. It's very clear what's happening. I don't think anybody's going to be confused about this. So we're going to load the PEM public key. Notice this is the same encoding, and it's a public key, and we've put the encoding here back together. Excuse me, so this is going to be text. And we're again going to use the default backend for this. Okay, so how do I prove that this works? First of all, if it doesn't crash, it's probably at least partially working. Let's do this and put it into a variable. Now, I'm going to put the text into a variable as well. Right. Key, and then I'm going to print the text, and I'm going to encode it and decode it, and then print that, and they should be identical. I'm actually going to do it like this so that I can show that it's identical without you having to eyeball every single letter, because that's no fun. So here we go. It's going to be the pub text of the text pub of text. Right, so we got this key, private key, we got the public key, we turned it into text, we printed that text, then we turn the text back into a public key, and we turn that public key back into text. So if everything is working and consistent, txt1 should equal txt2. Okay. Function object has no attribute public bytes. What line? 17. Function object. I'm passing as a function object somehow. Where is that? Ah, here we go. This is a function. I don't want to pass it a function, I want to pass it the key. So we can turn that key into text, then turn it back into a key. Something else. Add operand. Let's just check. Plus, yeah, here we go. One more plus sign than we really needed. Okay. A few teething troubles, but we have some success. Here is the original public key. Here is the public key that's been printed and then read back into an object, and they are equal. Success. So now we have the ability to create a key, export it as text, export its public key as text, and import that text back into a public key. So that's good. Now, some stuff that's actually going to mention cryptocurrency in a small way. One of the things that we have down here is our addresses are just strings that I made up. In Bitcoin, the address is the hash of the public key of that address. Okay, so it's going to be the public key, just to be clear. And now we have to get into using this library, in more than one line. So what we have to do is we have to create a hasher object, or a hash object. And I've decided, I don't know exactly what Bitcoin uses, but I decided to use this hash as my address hash. So what I'm going to do is I'm going to take the address here. Let me see, what did I actually do? Yes, that's what I thought. So I'm going to take this address, I am going to turn it into bytes, or text, and I'm going to hash it with this algorithm, which will result in a 224 character. Is it 224 characters or bits? 224 or something. It's shorter anyway than this guy. Another byte string of shorter length, which is going to be the address. So let's create our hasher object, which is a hash using the SHA-224 hash type, and we're going to use the OpenSSL backend for this. SSL backend. Okay. Now the way that we put the data into this object is with a update method. So hasher.update, and we want the pub text of this key. Okay. And then that will, if we finalize that, hasher.finalize. I already know this is not going to give us exactly what we want, but so be it. Let me just get rid of this extra stuff. I don't really need to print that. So I want the address that corresponds to this public key. And I also want to print that, obviously. Otherwise you won't be able to see what it is. What did I do wrong? Oh. This needs to be... no, it doesn't. I thought that would need to be instantiated. But no, apparently not. Ah, this needs to be instantiated. As you can imagine, this took me a little while to figure out when I was preparing for this. And the key is not valid. It's not there, that's why. There we go. So, again, this does not look like something that looks like an address. No doubt it's valid, but it doesn't look right. The reason it doesn't look right is because I need to encode it. And so what I'm going to do is I am going to use this guy, B64 encode, which will give us a nice ASCII alphanumeric string rather than this crazy thing. Okay, good. So now we have our address. Now what's next? Okay, so recap, private key is text, public key is text, rereading the text into a public key, and creating an address from a public key. So that's actually, when we do the transaction verification part, one of the steps is to look at the address and to look at the public key that is associated with spending that transaction, and make sure that the address is derived from that public key. So that's why it is that way. It's like an extra layer of making sure that all of the pieces fit together correctly. Now the other, slightly, in my opinion, more important part is the ability to sign the transaction. So I'm going to wrap this, where is it? Do we have it? Private key sign. Okay, it's a method on the private key. Sign priv key message, and again, if you just output the signature like that, you end up with something like this. So I'm gonna encode it again so that it looks nice-ish. Priv key.sign, and we need to send it the message, obviously, which is going to be an array of bytes, like all this stuff is. And we're going to specify that we're using elliptic curves and ECDSA, which is elliptic curve DSA, and the signature that we want is, again, SHA-224. Okay. Okay, let's do some printing. Sign private key and message. Let's see what that looks like. That's because okay, there's our signature. So that is or some version of that is going to end up in our transactions when we spend them. Yeah, well, so we also need to be able to verify them, obviously, which is, like here we're turning it into text and turning it back into a key, and similarly, there's two sides to the signature. You want to sign it and you want to verify the signature. Verify. And we verify against the public key and the signature and the message. So here we're taking a message and a private key and generating a signature unique to this message and this private key that can be verified by the public key that corresponds to this private key. And here in the verification, we're taking the public key that corresponds to this private key, the signature that we generated here, and the original message, and making sure that all those three things together agree. And if they do, then you can be sure to a very high degree of certainty that the person who owns that public key did indeed sign the message. So this guy actually throws an exception, and I know that's very Pythonic, but that's not exactly how I'm writing this thing. So yeah, the public key object has a verify method, and the verify method takes the signature, the message, and the hash type. So the signature is what comes out of here, but we need to decode it. bE64 decode signature and the message, and this exactly as it is, assuming that I balanced the parentheses, which I did not. Okay, and that is going to possibly throw an invalid signature error, and if it does that, we're going to return false, otherwise we're going to return true. And just as we did for the turning a key into text and back, I am going to sign my awesome message and then verify that the signature is correct. Alright, so there is my signature. And I want to print the verification. Verify, which is the pub. Oh, didn't want to do that. Pub key. Verifying the pub key against the signature and my awesome message, which will hopefully return true, but not in this case. What did I do? I am missing a parenthesis somewhere right there. But where? Could it be here? No. Yeah, it's here. There we go. True. And just in case you don't trust me, and I don't blame you, what I'm going to do is print the signature actually, just so we can see what's going on, and then I am going to mess with it. So I believe bytes objects in Python are not non-mutable, so I'm going to create a new one. Signature 24 plus bytes object of whatever it's not, which I'm going to say that it's not 0. Pretty good chance that I'll be correct, although I don't know why I'm looking at this, because it's going to be different because I'm generating a new private key every time. Signature 25 upwards. Okay. And so this should give me false. Yeah. So there you have it. So these are all of the operations that we are going to need in the next video, which is where we're going to bring these two parts together and make a transaction that is signed and verifiable, and add the signature verification to our verification chain algorithm. So then we'll really have proper Bitcoin-like transactions where you can be certain, to the extent that encryption allows you to be certain, that if you have a transaction that has been signed correctly, that you can verify that, and that the person who signed it is the holder of the private key. which really is the sort of one of the cornerstones of how cryptocurrency operates. Okay, so thank you for watching, and I'll see you next time.